Hi everyone, people starting to filter through. There we go, we're good. Just a test sample question. Look at this, we've got a friendly, helpful group here.
Okay, I dismiss everything for now, so that I clear it up and we will have more in the end.
Brill. Okay, cool. Okay, well, I'll kick off then. Thanks everyone who has who's joined us. For those of you that don't know me, my name is Barry Cranford. I'm the founder of the LJC and one of the organizers. So I founded it way back in 2007. Now I'm not a developer myself. I'm in fact a recruiter. I originally created the LJC as a way of establishing our name as Java recruiters, as I thought it might be a nicer way than cold calling. So I initially had plans to grow a group to what I thought was going to be a big 200 or 300. And here we are 13 years on with a group of 7,000, one of the biggest in the EU. But much more than that within the LJC, it's not just the numbers, but it's the real sense of community that we've always fostered. So it's just always been this place where everyone comes together to help everyone else learn and grow and that kind of thing. It's one of the things that I learned pretty early on, was just how much people are prepared to help everyone else in the tech community. It's amazing. So we've organized over 600 events now within the LJC. We've got 5 or 6, I think, that's still being booked. And it's all come from members just like Demos tonight, coming forward, helping out, giving out his time just to help you guys all grow. So the LJC's also helped us build other communities, like Meet and Mentor. So it's an initiative that we at RecWorks run. It's all completely free and just a way to help people that need to find help for their career, to get to the next step or learn particular technology, connect with mentors that can help them. So yeah, if you're interested in finding a mentor, you're interested in helping out anyone else, then please do sign up. Loads and loads of LJC members that are members on Meet and Mentor. Demos himself, I think, is a member on there as well. So yeah, and without further ado, then I will hand over to Demos. So for those of you that don't know about him or his work, he's currently with R3, which is the major contributor behind Corda. He's been working with R3 in the platform team for the last 2 years. And prior to that was with Amazon, working on Amazon Video and Alexa, I believe. So he spent much of his career working with the tech in the Java ecosystem. And with that, Demos, I'll hand over to yourself to take everyone through the rest of the presentation.
Cool. Thanks, Barry. Let me share my screen first. Yeah, hope you can see my screen now, right? Perfect. Let me start. Sorry. Yep. Okay. So today we'll meet Corda, which is a blockchain platform built for the JVM. And as Barry said, I work for R3, which is the major contributor behind Corda. So before we start, let's see like a brief agenda, what we will be looking at during today's talk. First of all, we will start with looking at an example problem. I'll try to follow a slightly different path in this presentation. Instead of starting by describing what the platform is, I will start by describing a problem that we'll try to solve by using the platform, hoping that this will give you a better understanding of what are the benefits from using this platform. So after we introduce this problem, we will go on and give a high-level overview of Corda, of the architecture and the key concepts, so that you can get a basic understanding of the various pieces. And after that's finished, we will proceed with a quick demo of the application that is built on top of Corda. And in the end, we'll do a quick analysis of the application, looking at the architecture, some basic diagrams, and I will also try and go through the code of the application. If you have any questions, please try to post them in the Q&A section, and I will try and have a look at them in the end. And also try and wait till the end, because some questions might be answered. So it will be easier to manage them in the end if they've already been answered. So with all that let's start now. So first of all, what is Corda? Corda, there's a big block of text here, but what this is essentially saying is that Corda is a platform for building distributed applications. And these applications, we call them Cordaps. And there are some special characteristics that Corda allows these applications to have that are written in bold here. The first is the fact that the various nodes that have these applications deployed do not have to fully trust each other. We'll see later what that means. The second one is that these nodes are able to transact with each other in a safe way, which means that the data consistency and data integrity is protected by the platform itself, and in a seamless way, which means that a lot of capabilities like authentication, serialization, performance, fault tolerance are taken care by the platform as well. The platform is written in Kotlin and runs on top of the JVM. And as a result, these applications that are built on top of Corda can be written in any JVM language in theory, but mostly they are currently written in Java or Kotlin, based on the patterns we've seen from clients. So let's move on now and see what the current landscape is, an example problem, and how it would be solved without using a platform like Corda. So we'll visit supply chain as a domain, and we'll use a very simple example where we have 3 companies that we will call distributor A, distributor B, and distributor C, that essentially interoperate to transfer some cargo items throughout the world. And the way we would typically solve that in the current state without using a platform like Corda is each company would build their own technical infrastructure, and they would have an API. That API could be an HTTP endpoint, a gRPC endpoint, or whatever the technology they choose. And of course, every company could have a different technology. And this is the reason they have different colors here. And each company would also have to implement a layer that would know how to communicate with the other companies. And in this way, they would all communicate, exchanging the data they need. And also every company would also have to build some business logic that would be responsible for knowing what kind of data are exchanged, what is their meaning, what is valid, what is not valid, etc., etc. And of course, we might have some discrepancies from company to company. This business logic might be slightly different, and that could cause, for example, problems in terms of data inconsistencies. So let's see some of the problems this architecture has. The first problem is we have an n-square integration problem, which means every company has to build these adapter layers for every other company, which is a lot of duplicate effort and duplicate code. The second one is business consensus, which means that as I mentioned before, the business logic implemented by every company will have some small differences. And as a result, we might have data inconsistencies because of that. So they won't have a shared view. Each company might view the data differently. The third one is authentication between parties. Every company needs a way to know that the company it's talking to is actually the company it's talking to and not a man in the middle or someone else. And they have to use specific protocols for that, like TLS or something else. And again, we might have different protocols between companies because of different policies. And that also becomes very complicated after a point. Another potential problem is dispute resolution. So because of these data inconsistencies we have between companies, there might be a point in time where companies end up having different data and they have to resolve a dispute. So for example, distributor A systems might see a cargo item as having arrived to distributor B, but distributor B systems might see that cargo item as still being in distributor A, and they have to resolve that dispute. And that sometimes can be quite tricky. Companies need to build a lot of auditing in their systems to be able to revisit historic data to understand what actually happened. And last one, but pretty important, is that the cost of introducing a new company in this network is pretty high, because that new company has to implement a lot of stuff that the other companies have already implemented, as we already discussed. So with that example presented now, let's go and have a look at what Corda is relatively quickly. I'll skim through the basic key concepts. So as we said, every node, we have multiple nodes that transact with each other. Every node essentially runs a JVM, and in that JVM, there will be one or more applications, what we call Cordaps. And these nodes all together form a network, as we see here. We see here, for example, 5 different nodes. And this network, there are some basic capabilities that this network needs to implement, which is permissioning and discovery. Let's see each one separately. The first one, permissioning, is the fact that there must be a process which the nodes need to follow to become part of the network, so that only allowed nodes are part of the network, and a way to also identify them. The way this is done in Corda is each node is identified by what we call an X500 name, which you can think of simplistically as the company's name, as a plain string. And each node has a public and a private key. They use the private key to sign data they send to other nodes as a form of attestation. And the public is used by other nodes to validate that data. And when a node wants to join the network, what happens is they create a certificate and they send it to a component of the network called the permissioning service, that essentially acts as a certificate authority, signing the certificate. And essentially, this certificate binds the X500 name of the node to this key pair, the public and the private key. And the second component, which is discovery, is the capability of the nodes to discover other nodes that are part of the network. And this is done by a separate service, which is called the network map, where nodes can make API calls that can be used to perform a lookup by the X500 name. And they will get back a lot of metadata information about this node, like what's the public key for that node, what is the IP address and the port the node is listening, etc., etc. So as we saw, essentially we have this network of nodes, and as a result, there is no centralized database. And in abstract terms, what's happening is we have all these nodes that want to represent the state of the world in some way. And we can think of this as a set of facts about the world. So what happens is some of the nodes will share some data depending on who needs to know about what. And it's not necessarily that all the nodes will have all the data, as it happens in other blockchain platforms, for example. And in this example, to give you a more concrete example, if we think about the supply chain I presented before, we can think one of those circles, the colored ones, represent, for example, a cargo item, right? And a cargo item that's been transferred between Alice and Bob, only those 2 nodes will have to know about it. The other nodes don't even know this data exists, for example. And these facts about the world are modeled in Corda with a concept called a Corda state. And the Corda state, as we see on the top left, has 3 main attributes. The first one is a reference to a contract. And the contract is a piece of code that essentially defines how a state can evolve through time. The second part is a field called participants that essentially determines which nodes need to know about the states and about updates to the state. And the third attribute, the third set is a list of attributes that are application specific. They are defined by the application, and they can differ depending on the application domain. So in this example here, we have this state represents an obligation, as we see, from Alice to Bob of £10 that needs to be paid by some date. And the participants of this state are both Alice and Bob, because they both need to know about this state and about any updates on it. And states in Corda are immutable, which means when a node needs to update the state of the world, what they do is they mark a state as historic. They essentially consume it, as we say, and they create a new state that replaces it. And as a result, as they all store all the states they've seen in their database, they will have a big set of consumed historical states, as we see in the top right, in the bottom right, and a smaller set of states that are the current one, the unconsumed ones, which is essentially the current state of the world. And this part of the database is usually called the vault. So when a node needs to perform this operation to update the state of the world, they do this via a concept called a Corda transaction. They form this transaction and they insert in it a list of input states, which are the states that will be consumed, and the list of output states, which are the states that will be created. They also add a list of commands that indicate the intent of the transaction, what kind of processing needs to be done on these states, and what kind of validation. And they can also specify a time window, which is a time window in which the transaction needs to be committed in order to be valid. There is a list of attachments, which can be references to the smart contract code or other documents like legal documents, or for example, CSV that contains some helper data. Every state also comes with a notary. And a notary, as we'll see later on, is a service that verifies some invariants that need to be maintained for a transaction to be valid. And of course, as I said previously, the various nodes sign a transaction as a form of attestation and approval. And what this transaction here represents is Alice paying part of that obligation we saw previously to Bob. So we have two input states here. We have the initial obligation from Alice to Bob of £10, and an initial state representing some money owned by Alice, £5. And the output states, which is the new state of the world, is the obligation, the new form of the obligation from Alice to Bob, which is now smaller, and it's only £5. And a state representing the same amount of money, which is now owned by Bob. And we have two commands in this transaction, a settle command and a pay command. And every command also specifies a set of nodes that need to sign this transaction. And as we see here, the settlement command needs to be signed by both Alice and Bob, because they essentially both participate in this obligation state and they have to approve any updates. But the payment command only needs to be signed by Alice, because the money is essentially owned by Alice. So only Alice needs to approve any payment, any transfer of the money. In practice, this is a bit more complicated than I presented it before, because the input states are not embedded in the transaction in this form. Instead, the transaction contains a reference to this state. And this reference consists of two fields. The first one is a transaction hash, which is the hash of the transaction that generated the state. And the second one is the index of that state as an output state in this transaction. And essentially, this keeps going on and on recursively. So these transactions form a transaction chain that will end in transactions that do not have any input state and only have output states. To give you an example, this could be, for example, a transaction that issues some cash on the ledger. So it creates some new money. And as I said previously, contracts are, a contract is a piece of code that validates a transaction. And in a transaction, we can have multiple states, and every state will reference a smart contract. And the platform is responsible of navigating all these references and making sure that all the contracts for a transaction are run. And if all of them indicate that the transaction is valid, then the transaction is deemed valid. If any of them fails, then the transaction is considered invalid. As I said, all the nodes that are participating in the network need to reach an agreement about the state of the world. And this is essentially what the platform helps with. And in Corda, we say we have two forms of consensus. The first form is what we call uniqueness consensus. And it is the fact that every state can only be consumed once. Because otherwise we would have a problem that is called the double spend. Thinking about the example with money, again, to give a more realistic example, if we say there is a node called node B that has some money in the form of a cash state, what this node could have done, for example, is it could have created two different transactions that contain this cash state as an input state, and essentially transfer it to two different nodes, node C and node D. And because these nodes would not be aware of the other transaction, they would both think that the cash is transferred to them. And in practice, what that would mean is that node B would have been able to spend that money twice. So this is something we want to prevent, of course. And this is prevented through a mechanism, through this service I mentioned before, which is called the notary service, which is a service responsible for validating transactions and approving them on the basis that the states haven't been consumed yet. This works in the following way. So every time a state is created, it is assigned a notary. And when a transaction is to be committed, first it has to be sent to that notary, and the notary needs to sign it. And the notary, of course, keeps track of all the states that have already been spent and rejects the transaction that try to spend them again. And the Corda architecture supports what we call the pluggable consensus, which means this notary service can have different forms. The more simple form, of course, is to just have a simple node with a database that stores all the spent states in the database and uses that data to approve and reject transactions. Of course, in some cases, we might want something that is more highly available, and we might use either multiple nodes on top of a single database in a master-slave architecture, or we can use algorithms from like academic algorithms for consensus, like Paxos or Raft. And this form, this is called CFT, notary, from crash fault tolerant, which means that if one of the nodes crashes, then it still operates. And there is also a more complicated form of notaries, which is called the BFT, from Byzantine fault tolerant. And these can also tolerate Byzantine failures of nodes, where these nodes can act maliciously or do things that are not compliant with the protocol. And this still works as long as these nodes are under a limit. The second form of consensus is what we call the validity consensus, which means that all the nodes that participate in a transaction should have the same view on whether that transaction is valid or not. And this is done. This is done first of all by running the contracts. So the contracts are supposed to be deterministic, and so if all the nodes run the contracts with the same transaction, they should all get the same result, whether the transaction is valid or not, regardless of the environment they run the smart contracts in, or the time when the transaction is validated, etc., etc. The second aspect that the nodes need to validate is that the transaction has all the necessary signatures. And this is done is they go through all the commands included in the transaction, and they sum up all the signatures, and they then check that the transaction is signed by all the signatures required by all the commands. But as we said, all the transactions form a transaction chain, and as a result, it's not enough for a node to just check that the transaction is valid on its own. It also has to navigate the references of the input states back to the whole chain and verify the historic transactions as well. To make sure, for example, so when someone transfers you some gas states, you have to make sure that these gas states are actually legit. So you have to follow the transaction chain up to the end and validate all the transactions from the issuance. And this is done dynamically as transactions are created and sent to the nodes. So it's not performance-wise, it's optimized. And this is the last thing we'll see about Corda in this section. Nodes, in order to do all this kind of processing we said, like create transaction, exchange them with each other, sign them, etc., they need to do a lot of communication. And Corda has created a framework that facilitates that, which is called the flow framework. And the flow framework provides some basic primitives that the applications can use to do things like exchange messages with each other. And it takes care of, so this framework takes care of a lot of capabilities, a lot of cross-cutting concerns that the applications don't have to care about, like authentication, serialization and deserialization of data, concurrency management, and fault tolerance. The APIs provided by the framework are blocking, appear to be blocking to the application. So for example, when the application does a receive operation, it will look like as if the application is blocked at this point until the node receives a message by the other node. But in reality, what happens is this flow will be suspended and another flow will be executed until that message arrives, when that flow will be scheduled to be run again. And also when this suspension happens, the node will also checkpoint this flow and store it in the database for fault tolerance. So in case the node crashes and restarts, the flow will be able to restart from the last checkpoint instead of starting it from the beginning. So I see there was a question here. Okay, let me finish and I'll come back to the questions. So we'll go back and look at the, sorry, let me start the slideshow again. Yeah. We'll go back and look now how we can solve the same problem using a Corda application instead of what I presented before. I have created here a demo. I recorded it. I know it's kind of cheating, but I just wanted to have the optimal experience for you. And I hope this will help you get a high-level understanding of what the application looks like before we go and see what the code is, etc., etc. And what we have here is we have 3 tabs in a browser. Every tab is essentially connected to the systems of one of these companies. So we have one for company A, one for B, and one for C. We have a table with shipments. There is no shipments currently, as we see. And I'll go here in distributor A and create a new shipment. For example, I will select the other nodes that will participate in the shipment, A, B, and C. I will create the shipment. This essentially is a new state in the ledger. We get the ID back, and we see that in the table the shipment now. Now we'll go to the other nodes. We also see they have this data as well. And we can go in node B now and say that the cargo has arrived to us. This updates the state of the world with a transaction, and we see the other nodes see the same thing now. The cargo item is in distributor B. And then in C, we can do the same, and also then deliver the cargo item to the end recipient. And this essentially will exit the state from the ledger. And we see now that all the nodes have ended up having the same view, which is what I described as consensus before. So this was the demo, the quick demo. Let's have a look at the architecture now. So this is the architecture of what I demonstrated just now. We have 3 companies. Every company was running a Corda node, and with a Corda deployed. The Corda essentially, there were 2 Cordas in fact. There was one Corda that contained all the states and the contracts, and there was a separate Corda that contained the flows. That's a common practice, splitting the flows from the states and the contracts, because these concepts evolve slightly differently, so it's better to have them separated. Each company was also running a web server that was communicating with the Corda node and was triggering flows, and also retrieving data to show to the user. And I used a Spring Boot application for this. Of course, every company could have a different web server and different application, a different front end, etc. But for simplicity here, it's all the same. And something that wasn't visible in the demo was there was also a notary running, where all the nodes were sending the transactions for them to be signed before they are committed. So let's have a look at the structure of the state and the flow, and then we'll go and have a look at the code. So in this Corda, we have a single state, which represents a cargo item, and it has 3 different fields, as we can see here. The second one is just an identifier, a unique identifier for the cargo item. The first is the list of distributors that take part in this shipment. And the third field is the current distributor, where the cargo item is located, essentially. So what happens is the node that creates the shipment creates a transaction that has a single output state, the new cargo item that is issued on the ledger. And then node B, for example, when it wants to notify the other nodes that it has received the cargo item, it creates a new transaction with the old state as an input state, and the new state that has all the same fields, except the current distributor that now points to node B. And that keeps going on until the last node needs to deliver the cargo item to the end recipient, to an actual customer, for example, that's not part of the Corda network or anything. And then it creates a new transaction that has that state as an input state and no output states. And sometimes we call that this process as the state exiting the ledger. Let's also have a quick look at the flow. We'll look at there are 3 flows, in fact, in this Corda, but we'll look at the one that is used when a cargo item is transferred from a node to the next node. And this is called the arrival flow. So what happens is the operator, for example, in the physical world, receives the cargo item and then goes on to the web frontend and triggers that button we saw. That will trigger a flow in the Corda node with a specific cargo identifier. And the Corda node will perform an SQL query in the vault, in the database, using that identifier to retrieve all the state information. And using that state information, it will build a new transaction with this state as an input and the appropriate output state, and the commands. The commands here will just be a single transfer command. It's pretty simple. And it will then sign the transaction, essentially approving the fact that I actually received the cargo item. It will then send the transaction to the previous node where the cargo item was previously located. That node will check the transaction that it's valid, and then after that, it will also sign it, approving again that, okay, I delivered the cargo item to you. And after that point, it will send the transaction back to node B. And the node B now needs to, the transaction has all the required signatures from the previous distributor and the new distributor. And what needs to be done is it needs to be signed by the notary. And after that point, it will be considered final, committed, let's say. We call this process finalization of the transaction. So the node sends the transaction to the notary. Hope that's not, yeah, it's not obstructing you. So we see down here that the node sends the transaction to the notary. The notary performs some checks to verify that the transaction, the input states haven't been spent yet. And then it signs the transaction and sends it back to node B. And after that point, the transaction is now considered committed, and the node B just broadcasts it to the other nodes. And I think at this point, you all think, okay, all this talk is good, but now let's see some code. So that's what I'll try and do. So I have here, I've opened here the project that essentially consists of three main parts. This Corda module, it's based on Gradle, and we have three Gradle modules. The Corda module contains the Corda that contains the flows. The Corda contract states contains, of course, the states and the contracts. And this clients module contain essentially the web app I talked about. So let's start with the states and the contracts. Yeah, let's open this one. Okay. Let me zoom in a little bit. I hope that's okay for you now. If you're having any issues, just post a comment in the Q&A. It seems it's okay. So we see here the cargo state I talked to you about, and it has three fields. It has a field called participating distributors, which is a list of nodes that participate in the shipment. It has a cargo ID field, which is the unique identifier of the cargo item. And it has a field called current distributor, which is where the cargo item is currently located. And there are a few more things. We'll talk about them a bit later. We'll skip them now. What we also see is there is an annotation here called belongs to contract, which is essentially the reference I talked to you about from the state to the contract that governs how the state needs to be evolved through time. So if we go to that class, the cargo contract, we see that essentially a simple class with a single method called verify that receives a ledger transaction. That's essentially a Corda transaction, and it either executes successfully, which means the transaction is valid, or it throws an exception, which means the transaction is invalid and should be rejected. And we see, and there are, Corda provides a DSL that can be used to perform some validation in a fluent way. So we can have a quick look here to see how it looks like, and a simple contract. First of all, this contract verifies that there is a single command in the transaction. And as we see, there are three different types of commands. You can scroll down here and see them. There is a command called enter, which is when we create a new shipment and we enter a state in the ledger. There is a command called transfer, which is used for transferring the cargo item to the next node. And there is a command called exit, which is used when we deliver the cargo item to the end recipient. So if we go back to the contract, we'll see that there is a conditional for every command that performs different validations. And let's have a look at the transfer here, which is what we've talked so far about. We see, for example, here it collects the signers, the required signers from the transaction, the input states and the output states, and it uses one of the APIs of that DSL to ensure that there is only one output state and only one input state in the transaction. And this is essentially the string that will be shown as an error if the transaction is invalid. And another validation is, for example, the fact that as we see in the message here, the transaction needs to be signed by both the sender and the recipient, as we saw previously. And the way this is checked, if we look at the code, is by checking that the signers, which is what I showed previously, contains the key of the current distributor of the output state and also the current distributor of the input state, which is essentially the previous and the current distributor. So I'll go back now to the state and we can have a look at the rest of the stuff. So we can see that this state implements an interface called queryable state. And this is because in Corda, all the states are stored as blobs by default. And they can only be queried in a specific way. But in Corda, if you want, you can query them in other ways, and you can also index them since they're actually stored in an SQL database. And this interface performs this, allows this capability. The way you do it is you define a new class, which is essentially a JPA entity. In this case here, this is the persistent state. And you also define a mapping from the actual state to that JPA entity. And then the platform does everything. So if we go and look at the state, let me zoom in a little bit. We'll see that it's a normal JPA entity. JPA is the Java Persistence API. And Corda uses internally Hibernate. And we see that it specifies that it's a JPA entity, the table where the state will be stored, and for every one of the fields, what is the column of the name, etc., etc. And here you can have also additional annotations that can specify what kind of indexes exist, for example. Okay, having finished with the contract, I think we can now go and have a look at the flow. Let's look at the arrival flow, which is what we saw in the diagram before. Let me zoom in a little bit. So this is the arrival flow. It has a single parameter, the cargo identifier, as we saw before. And it implements this, it extends this class called flow logic from Corda that has a single method called call that performs all the business logic. This is essentially the sequence diagram that I showed you. And what happens here, you can have a look in more detail on your own later on, but what happens is, as we saw, it performs initially an SQL statement to retrieve all the data of the state, and then it proceeds to create a transaction using this state as an input state, and as an output state, the same data with a new distributor, and also adding the necessary commands, which here is a transfer command and the keys that need to sign it, which is the current distributor and the previous distributor. Then it signs the transaction, and then it has to, as we saw, it has to notarize it and send to the other nodes. But before doing that, it has to collect signatures from the other nodes. So in order to do that, this flow will send an initial message to the parties indicating the role in this flow, whether they actually need to sign the transaction or just receive it after it is finalized. And as we see here, the way this is done is it creates a session with all the other nodes involved in the transaction. And then it has this message called transfer role that can be either a participant or a signer. And it sends the role of a participant to all the nodes except the previous node that has to sign it. And then it sends to the previous node the role signer. If we look at this class, actually, we see that it's actually an enumeration that has two values, and it has this annotation, Corda serializable. And that's all we need to do to send a message in Corda. Everything else is taken care of by the flow framework. It knows how to serialize this data and also deserialize it when it receives it. So if we go back to this point, it sends first this role, and then at this point, it is ready to collect signatures from the parties that need to sign the transaction, and then send it to the notary. And the platform comes with some basic flows that can be reused. And for this reason here, this flow makes use of this flow, the platform flow called collect signature flow, that essentially does this thing. You specify the transaction and the nodes, and it collects the signatures. And we get back a signed transaction. And after that, we call a different platform flow that is called finality flow, that essentially sends the transaction to the notary and receives it back and then broadcasts to the other nodes. So it's pretty concise. It's a few lines of code. And we also need to implement a flow that will be triggered on the other nodes as a response to the initial flow. And this is what is called here the cargo arrival responder flow that is annotated by this annotation called initiated by, that points to the flow that will trigger it, essentially. And here it's even smaller, as we see. This flow essentially does a receive in the beginning, waiting for this initial message that indicates what kind of role this node has in the transaction. And after receiving this role, there is some conditional depending on whether the node is actually a signer or a participant. If it's just a participant, it will call the finality flow that just waits for a transaction that has been finalized. If it's also a signer, before doing that, it calls a signed transaction flow that receives a transaction, checks it, and signs it back. So depending on what kind of node this is, it will perform different logic. And before closing that, let's quickly go to the web app, just to have a quick look at that as well. It's a regular Spring Boot app with 3 or 4 endpoints. They're pretty simple. So it's a regular REST controller, and we can have a quick look at the endpoints. We have an endpoint at /parties that returns all the parties in the network, and this is used in the front end when we want to create a new shipment and we want to see which parties we can include. There is a schedule create endpoint that is used for creating new shipments. And as we see, this creates, as we see here, this creates a new flow in the Corda node called enter cargo flow. There is a /cargo endpoint that essentially returns all the cargo items, and it's used to populate this table we saw in the demo. And then we have 2 more endpoints that are used to to create a transaction when a cargo item is received, and also when a cargo item is delivered to the end recipient. And all this does is it triggers, as we see here, a flow on the Corda node, either an arrival flow or an exit cargo flow. So this was all the code. And now that we've seen the architecture and what the code looks like, we're gonna have a quick discussion about what benefits we get out of this, and then we can go to questions. So the first benefit is easier integration because of this shared protocol. Part of it is the flow framework that gives a lot of things out of the box. And as a result, the various nodes don't have to re-implement stuff like define serialization and deserialization formats or do authentication, etc., etc. On On top of that, we have business consensus because we have some shared logic across the various nodes through this Corda. And through the concept of notaries, we can also ensure that data are evolved in an organized way, preventing double spends and other anti-patterns. The third benefit is, as I already mentioned, a thing like authentication, which can be quite complicated, is provided out of the box and it's very easy to integrate with. We have easier dispute resolution because now, as we saw, all the nodes sign the data as a form of approval. And that signature can be used to resolve disputes. For example, if we think about the scenario I described before, where node A and node B have different view of the data, what can happen is if node A has a transaction that has been actually signed by node B, that shows that the cargo item has actually been delivered to node B, then this data can just be used to resolve this dispute because it proves that actually node B has received the cargo item. And the last one is there is a lower barrier to entry for new participants because for a new company to enter this network and interoperate with everyone, they don't have to implement a lot of new code to integrate with the other companies. All they have, they can just deploy a new node, provision a new Corda node, and deploy that existing Corda up there. And right after that, they're able to interoperate with all the other nodes. For everyone that is curious and wants to have a further look on that, I added some links here. The first two are the link to the public documentation of Corda, and the second one is a link to the GitHub repo of the open source project. And the last two are, the third one is the link to the application I demoed. And the last one is a blog post I wrote that gives a more elaborate explanation about the application for those of you that are curious. And with that, I think we reached the end. So I will now go back to the Q&A section. And I will have a look at your questions. So the first question by Anil is, what about performance? As far as I know, blockchain is used for data sharing securely. Can we use it for generic distributed system? For example, the supply chain model you described in the example. So Corda, when compared to other blockchain platforms, Corda has better performance thanks to various aspects of the design. For example, as I mentioned before, not all the nodes will have all the data, so there is no public broadcast here. The data are only shared with the nodes that need to know about it, and this is a lot more scalable. And there are also other aspects that help with performance. For example, the fact that different states can have different notaries means that we can do very efficient partitioning. So we can partition our data sets across different notaries and prevent notaries from becoming bottleneck. There are a lot more aspects that help with performance, but this is potentially a separate talk altogether. If you go and look on the documentation, you will see there is a lot of documentation actually about performance, and this might be helpful to you. So second question, okay, I answered that. Second question by Anthony. You have mentioned that Corda supports a Byzantine fault-tolerant consensus algorithm. What percentage of the nodes needs to be compromised before the solution is compromised? So this depends on the algorithm you will use, but there are, I think there are some lower bounds for every algorithm because of some impossibility theorems. And if I recall correctly, these lower bounds are the following. If you have, let's say, in order to be able to tolerate n malicious nodes, you need to have a set of 3 n+1 nodes. This is quite complicated stuff. One of these algorithms, for example, if you want to go and look, is the PBFT, it's called, Practical Byzantine Fault Tolerant. And it's slightly different to Bitcoin, as I described. The model is also a bit different because in Bitcoin, we have what we call probabilistic consensus, which means when a transaction is validated by some miners, this is not essentially final, because that transaction can potentially be reversed. If, as you say here, more than 50% of the network think that this is not the case, they can actually reverse. They can create a longer chain and reverse that transaction. And this is why it's called probabilistic consensus, because as more and more nodes approve that, it gets harder and harder. And the deeper this transaction is in a chain, the less probable it is it will be reversed. While in Corda, after a transaction has been finalized by a notary, it cannot be reversed. If it is reversed, it is something that is against the protocol, and someone can legally pursue that notary service because they have done something wrong. So I'll close that as well. Oh, cool. See more questions coming in. Is there any concept need of mining? So that touches a little bit on what I mentioned before. There is a need to approve transactions, and in this concern, Corda is slightly different to other blockchain platforms. Other blockchain platforms have the concept of miners. They are what we call permissionless blockchains, because any node can take part in the network. And as a result, anyone can validate transaction, anyone can be a miner. And for this reason, this also means that this validation is a bit more weak, we could say, for example, because everyone that has a lot of nodes can get control of the network and reverse transactions, for example. Corda is what we call a permissioned blockchain, which means only nodes that have been allowed access to the network become part of the network. And in the same way, the notaries are also approved, are pre-approved. So we can get bigger assurances about validation of transactions because we know who the notaries are. And the notaries have to guarantee that they follow the protocol, and they will reject transactions that are not valid, for example, because an input state has been double spent. And in terms of, if we think mining also has a different function of generating new coins, for example, in Bitcoin. In Corda, we don't have that notion because there is not really a cryptocurrency. If we want to create new money, we just issue it in the ledger. So there is no real need for mining because of this reason. Last question is, what is current adaptation on the market? I guess that's a question about adoption. Correct me if I'm wrong. There is, during the last years, we've seen actually a lot of people switching from permissionless blockchain platforms to permissioned blockchain platforms like Corda or Hyperledger Fabric, because of the security guarantees that I described before, the difference between probabilistic finality and deterministic finality, and because of other characteristics as well, like privacy, the fact that in some permissionless blockchains have to do public broadcast and share the data with everyone, while in Corda you can only share it on a need-to-know basis. And as a result, it's also applicable in a lot of different industries. So if you're curious about that, I would say if you visit the website of R3, there are a lot of case studies from companies that used Corda successfully, and you can see you can find what things that would interest you, perhaps depending on what kind of business domain you're interested in. In a highly sensitive use case, does Corda provide any method to use for encrypting data before it is made part of a transaction? Or is this the job of the application side? So when nodes communicate with each other, they will do that in a secure way. They will, as I said, they will do it under TLS. So everything is encrypted in transit. But transactions themselves are not encrypted by default, because the nodes need to be able to read the data in them. And depending on some scenarios, you can have, there are a lot of different configurations. For example, if you want, you can also have notaries actually read the transaction and run the smart contracts. In some cases, you might not want to do that. So that's not provided by the platform out of the box at the moment. What you can do is you can either do it at the application side, potentially, or of course you can use capabilities of relational database so that you set the proper controls when the data are stored. And I think some of the database also support encryption, so you can store the data at this level potentially. But the platform doesn't provide encryption of the transaction data by default. Cool. And I think with that, I think we arrived at the end. There are no more questions. So thanks everyone for joining. Will this recording be shared? I have to talk with Barry. I'm not sure if he actually recorded it. If he did, I'll ask if we can share it. I'll go and ask now after I close this session. Okay, so thank you for the session. Okay, thanks for joining everyone. I hope you enjoyed it. And I hope you stay safe and are well. Have a good night.